Imagine a time when our universe, everything we see and know, was compressed into a point smaller than an atom. This point, known as a singularity, was unimaginably dense and hot, containing all the matter and energy that would eventually form everything around us. This dense, hot entity, called a singularity, contained the seeds of all matter and energy. It was a state of infinite density and temperature, a cosmic cauldron brimming with potential. Then, about 13.8 billion years ago, this singularity exploded in an event we call the Big Bang. This monumental event marked the birth of our universe, setting everything into motion. This wasn't an explosion in the traditional sense, like a firework in the night sky. Instead, it was a rapid expansion of space itself, a phenomenon that defies our everyday experiences. Instead, it was the rapid expansion of space itself, an expansion that continues to this day. Space didn't just expand, it stretched, carrying galaxies and stars along with it, creating the vast universe we inhabit. The Big Bang Theory is currently the best model we have to explain the origin and evolution of our universe. It provides a comprehensive framework for understanding how everything began and how it has changed over billions of years. It's supported by a wealth of observational evidence, from the cosmic microwave background radiation to the distribution of galaxies in the universe. These observations give us a glimpse into the early moments of the universe and its subsequent development. This theory helps us understand how our universe evolved from an extremely hot, dense state to the vast and complex cosmos we observe today. It explains the formation of galaxies, stars, and planets, and ultimately, the emergence of life itself. In the first fleeting moments after the Big Bang, the universe was an inferno of unimaginable heat and density. Temperatures were so high that matter as we know it couldn't exist. Instead, the universe was a sea of pure energy, a chaotic soup of fundamental particles and forces. During this epoch, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single force. As the universe expanded, it cooled rapidly. This cooling allowed for the separation of the fundamental forces, a process that unfolded in stages. The first force to separate was gravity, followed by the strong nuclear force, and then the weak nuclear force and electromagnetism. These separations were crucial for the formation of the universe as we know it. As the universe continued to cool, energy began to condense into matter. This process, governed by Einstein's famous equation E equals mc squared, marked a significant turning point. The universe was no longer a sea of pure energy, but was now populated by fundamental particles like quarks, leptons, and their antiparticles. These particles, the building blocks of all matter, collided at high speeds, constantly being created and annihilated in the intense heat. The universe was a chaotic dance of particles, a cosmic ballet driven by the laws of physics. This early period was marked by a delicate balance between matter and antimatter. For every particle of matter, there existed an antiparticle with an opposite charge. When a particle and its antiparticle collided, they annihilated each other, releasing a burst of energy. Around 380,000 years after the Big Bang, the universe cooled enough for protons and neutrons to combine and form the first atomic nuclei, primarily hydrogen and helium. This marked the beginning of a new era in the cosmos, where the building blocks of matter started to take shape. However, the universe was still too hot for electrons to bind to these nuclei. The intense heat kept electrons in a free state, preventing them from forming stable atoms. Instead, electrons existed in a free state, scattering light and making the universe opaque, much like a dense fog. This scattering of light by free electrons created a dense, impenetrable environment. As the universe continued to cool, a pivotal event occurred. Electrons combined with atomic nuclei to form neutral atoms. This process was crucial for the universe's evolution, allowing it to transition to a more stable state. This event, known as recombination, transformed the universe from an opaque plasma to a transparent state. The recombination allowed light to travel freely, marking a significant turning point in cosmic history. Light, which had been trapped by the free electrons, was now free to travel through space. This newfound transparency allowed the universe to be illuminated in a way it had never been before. This first light, now stretched into microwaves due to the expansion of the universe, is what we detect today as the cosmic microwave background radiation. This ancient light provides us with a glimpse into the early universe. offering invaluable insights into its origins and evolution. Section 5. The rise of stars. Gravity's crucial role. After the formation of atoms, the universe entered a period known as the Dark Ages, a time before the first stars ignited. Gravity, however, was at work, subtly pulling together the slightly denser regions of hydrogen and helium gas. Over millions of years, these regions became denser and denser, eventually collapsing under their own gravity. The immense pressure at the centers of these collapsing gas clouds caused temperatures to soar, reaching millions of degrees. These extreme conditions triggered nuclear fusion, the process where hydrogen atoms fuse to form helium, releasing vast amounts of energy. And so, the first stars were born, illuminating the universe with their brilliant light. Section 6. Galaxies emerge, islands of stars in the vast cosmos. The first stars were massive and short-lived, ending their lives in spectacular supernova explosions. These explosions enriched the surrounding gas with heavier elements, the building blocks of planets and life. Gravity continued to shape the universe, drawing together stars into vast collections called galaxies. Galaxies come in a variety of shapes and sizes, from majestic spirals to massive ellipticals. Our own galaxy, the Milky Way, is a barred spiral galaxy, home to billions of stars, including our own sun. Galaxies are not randomly scattered throughout the universe, but are instead organized into clusters and superclusters, forming a vast cosmic web. Section 7. The universe's accelerating expansion, a mysterious force. For decades, astronomers believed that the expansion of the universe was slowing down due to the gravitational pull of matter. However, in the late 1990s, two independent teams of astronomers made a groundbreaking discovery. The expansion of the universe is not slowing down but is actually accelerating. This discovery sent shockwaves through the scientific community. What could be causing this acceleration? The answer, it seems, lies in a mysterious force called dark energy. This enigmatic force, which makes up about 68% of the universe's total energy content, acts as a sort of anti-gravity, pushing everything apart. Section 8. Dark matter and dark energy, unseen players on the cosmic stage. While dark energy drives the universe's accelerating expansion, another enigmatic component, called dark matter, plays a crucial role in the formation of galaxies and galaxy clusters. Dark matter, which doesn't interact with light, makes up about 27% of the universe's total mass. Its gravitational influence holds galaxies together, preventing them from flying apart. Together, dark matter and dark energy make up a staggering 95% of the universe's total mass and energy. This means that the familiar matter we see around us, from stars and planets to galaxies, accounts for only a tiny fraction of the universe's total content. Section 9. Looking back in time. Telescopes as time machines. Astronomers use a variety of telescopes, both on Earth and in space, to study the universe. These telescopes act as time machines, allowing us to observe distant objects as they were in the past. This is because light from these objects takes time to reach us. By studying the light from distant galaxies, astronomers can learn about the early universe and how galaxies have evolved over billions of years. Space-based telescopes such as the Hubble Space Telescope and the James Webb Space Telescope provide us with breathtaking images of the cosmos and allow us to peer deeper into the universe than ever before. Section 10. The future of the universe. Endless possibilities. The future of our universe is uncertain and depends on the interplay between the expansion driven by dark energy and the gravitational pull of matter. These forces shape the cosmos in ways we are only beginning to understand. One possibility is that the universe will continue to expand forever, becoming increasingly cold and dark as galaxies drift farther and farther apart. This endless expansion would result in a universe where stars burn out, leaving behind a vast, empty void. This scenario is known as the Big Freeze. In this cold and desolate future, the universe would be a shadow of its former self, with only remnants of galaxies remaining. Another possibility is that the expansion will eventually reverse, leading to a big crunch. This dramatic event would see the universe collapsing inward, galaxies converging in a cataclysmic implosion. In this scenario, the universe would collapse back on itself, potentially leading to a new Big Bang. This cyclical model suggests that the universe could be reborn from its own destruction. Other possibilities include a big rip, where the expansion of the universe accelerates so rapidly that it tears apart all matter from galaxies to atoms in a violent and chaotic end. And a big slurp, where a quantum fluctuation creates a bubble of true vacuum that expands at the speed of light, destroying the universe. Each of these scenarios presents a different vision of the ultimate fate of the cosmos, reminding us of the vast and unpredictable nature of the universe. Section 11, The Ongoing Quest, Unraveling the Universe's Mysteries. Despite the remarkable progress we've made in understanding our universe, many mysteries remain. What is the nature of dark matter and dark energy? What happened in the first moments after the Big Bang? Are there other universes out there? Scientists are constantly pushing the boundaries of our knowledge, developing new technologies and conducting groundbreaking experiments to answer these fundamental questions. The quest to understand our universe is a journey of discovery, a never-ending exploration of the cosmos and our place within it.